Good morning to all. Can you hear me? Hello. My voice is clear to you all? Okay. Now, let me present my screen to you all. Okay, now listen. In last lecture, I have explained you RSA algorithm. Now, not RSA algorithm, but regarding that one example that I have discussed. So today, first of all, I will give you idea regarding that RSA algorithm, and then after I will explain the next topic. Now, see in RSA, before I explain you that RSA algorithm example, see I told you that concept that is in public key crypto system. What happened if there are two party, one is a Alice and another is a Bob. If Alice want to send some message to a Bob, then who perform the key generation setup? The Bob perform the key generation algorithm. And now, when Bob perform a key generation algorithm, so at that time we can say that the private and public key, these two pairs are generated on receiver side, means Bob side. Now after that, what the Bob will do? Now Bob sends a public key to a Alice, and here in Alice side, whatever the plain text is there, with the help of this public key, the Alice encrypt the message. Now after that, what happened? So in Bob side, what happened? So once the encryption is done, the this cipher text that is sent to the Bob, and with the help of this private key, just wait everyone. Hello, take a wait. Hello. Okay, so now what happened? So now public and private key that is generated on Bob's side. Now what the Bob will do? So this public key send it to the allies, and with the help of this public key, what the allies will do? Encrypt the message. Now, so after that, the ciphertext is generated. Now this ciphertext is sent it to the Bob, and then with the help of its private key, now what the Bob will do? Get the original message, right? So these regarding the public key crypto system that I have explained, right? And one of the point that you have to remember, that is the symmetric key algorithm are generally known as a secret key, and the private key is used in asymmetric key cryptography. This is the term that you have to remember. Now, then after RSA algorithm that I want to explain you. So that is it is the most common algorithm, and it is named for its inventors Ribest, Samir, and Adleman. Okay, so these are the three inventors are there. Now, the idea is that the RSA uses a modular exponentiation for encryption and decryption. Hello, can you hear me? Okay. So now the RSA uses a modular exponentiation for encryption or decryption. Now here the E is used for encryption key, or you can say public key, and D is used for decryption key or private key. So these are the terms that you have to remember. E is for encryption key and D is for decryption key. Okay, so this is the term that you have to remember. Now, see that point that in your example that I have discussed, if Alice want to send some message to a Bob, then Bob perform the key generation setup and generate the private and public key. Now, the reverse case, if Bob wants to send a message to Alice, then Alice perform the key setup. Right, so here you can say that you have to assume Alice want to send some message to a Bob, means Bob perform the key generation, Bob perform the setup. So now initially in RSA algorithm, see, initially you have to select the two large prime number p and q such that p not equals to q. Okay, so now see in our example, we have taken very small number for our conveniency purpose. But see, in real life, what happened in RSA, the two large prime numbers are taken, and see in your implementation when you perform this program in a lab session. So what happens? So user can enter the any number. User can enter the any number, any value of p and q. So at that time, see in next lecture, I will explain you Miller or format test primarity. So with the help of this test, whatever the number you are entering, right, you have to check with the help of this particular algorithm. You have to check whether these numbers are prime or not. And once it is prime, then you can say that this particular numbers are considered for RSA algorithm. Okay, so whenever the user enter the any number, so first of all, this by using this algorithm that you have to check whether the number is a prime or not, and once the number is prime, then you can say then you can apply the RSA algorithm, right? So in this way, in lab session you have to perform the implementation. Now then after, see what is the second step of key generation algorithm. So initially you have taken large prime number p and q. Now then after you have to perform n equals to p into q. Now the next step is phi n, that is equals to phi in bracket p cross q. Right. So instead of that, all of you know that you can write phi p into phi q. And see the Euler's this Euler's rule that already that I've explained. If p is a prime, so instead of this phi p, I can write p minus 1, and instead of this phi q, I can write q minus 1, right? So in this way, you can write. Now, what is the fourth step of RSA algorithm? So what you have to do? You have to select E such that what you have to check. So you have to see here the phi n that you have calculated. So now you have to find a value of E such that the GCD of E and phi n is 1, right? So that means the meaning is that E and phi n are co-prime. This is the fourth step of RSA algorithm. Now then after, what you have to do? So you have to calculate D equals to E inverse more phi n. E inverse more phi n. So by using the extended Euclidean algorithm, you have to calculate it. Up to this clear, everyone? Is it clear to you all? Okay. So now see here after this what happened? So the two keys are generated. One is a public key and another is a private key. These two keys are generated, right? So now what happened? If Alice wants to send a message to a Bob, Bob perform the key setup, and by based on that, using this RSA key generation, what the Bob will do? The Bob generate the public key and private key. Now once it is done, after that, what the Bob will do? The Bob sends a public key to a allies. Okay, so this is the next step of RSA algorithm. So now see here, instead of this n, you have to consider P and Q. Again, I repeat, here in RSA algorithm, the public key is what E and N, and private key, see N is a public key. Instead of that, here you have to write P and Q. So P, Q, and D, these are the private key. Okay. Now then after, what happened? So now once a public key is generated, the Bob sends a public key to a allies. So now when Bob sends a public key to a allies, so now M is a plain text, right? So the that is entered by the what allies. Okay. Now whatever the plain text is there, with the help of this public key, what the allies will do? Encrypt it, and for encryption, this algorithm that you have to calculate. So m that this equation that you have to use, m raised to e mod n. All of you know that. And c equals to m raised to e mod n. So using the multiply and square method, what you can say, you are getting the ciphertext. Now once you get the ciphertext, then all of you know that with the this ciphertext is sent to the Bob, and Bob, with the help of its own private key, the Bob decrypt it. So for that, this equation that you have to use, m equals to c raised to d mod n. Up to this clear, everyone? Is it clear to you all? Okay. Okay. Now, see here, the M is a plain text. The M is a plain text, that is the number corresponding to a text. See, normally in asymmetric cipher that use with the number. So in exams, mostly the plain text that I am giving in a number. But suppose let's say if the plain text, if the something text is given to you, then corresponding to you have to take a number. Okay, suppose let's say I can say that suppose I am giving the plain text C. So all of you know that corresponding to C, what is the number? Can anyone tell me? Corresponding to C, what is the number? Corresponding to C, what's the number, everyone? Hello? Corresponds to C, what's the number that I am trying to say? Can you hear me? Hello? Can you hear me? Hello? So whatever the plain text is given corresponding to, you have to take the number. Okay. So now, why is that correct? See, first of all, today I want to prove in a decryption algorithm. See, in for decryption, what is the equation? C raised to D mod n, right? So in a decryption, how you can get the n? In decryption, how you can get the n? So through this theory, I want to explain you how we are proving this n. Okay. So now, first of all, what you have to do that I want to explain. So see, we know from the key generation algorithm, we know that. See, I'm writing in whiteboard so you can understand. Just wait. My screen is visible. Hello. My screen is visible, everyone. Hello. Please reply in the chat window. Okay. Now, see, now next I will show you a proof. So actually, in cipher, sorry, in decryption, when you perform the decryption, how you get the original message. So regarding that, one proof is there. So there, but for that, before I explain you decryption portion, I want to tell you one point. Just see here. Now, now see, we know from key generation. With this equation, we know that is D equals to E inverse mod phi. Right? All of you know this equation. Now, what I'm doing here, both the side I am multiplying with E. So what I get E into E inverse mod phi n. Right? So now, here what can I write? ED, E into E inverse, that is 1 mod phi n. You can write it this way. Right? Now, see, all of you know that here when I perform when I perform ED by phi n, so how can I do? So if I write here ED by phi n, so I am getting K such that I can write in this way, right? So here I can write ED equals to 1 more phi n. So now if I perform ED by phi n, so I'm getting some some k integer such that I can write in this way ED minus k phi n, that is equals to 1, right? So that's why here I can write in this way. Just wait. So here I can write in this way ED equals to sorry, ED minus k phi n that is equals to 1. Therefore, I can write in this way ed equals to k phi n plus 1. Okay, so now ed equals to k phi n plus 1. So now here instead of that, can I write like this? Ed that is equals to k phi n plus 1 where k is integer, right? Now, so now at the decryption side, I am telling you about at decryption side. So now see, first of all, you have to just I am proving why, and see, just through this particular sorry, through this I want to explain you how you are getting the end, means at the decryption side, how to achieve the plain text, that I want to explain you. So now what happened? Now at decryption, what happened? Now see here. Now at decryption, all of you know the decryption equation, that is C raised to D mod n, right? So instead of C, what can I write? Can anyone tell me? Instead of C, what can I write? All of you know the encryption equation. Please write down in your chat window. What is the equation for encryption? Hello? Can you hear me? What is the equation for encryption? M raised to E mod n, right, Rikit? Abhi. So instead of that, I can write in this way m raised to E mod n raised to D mod n, right? So now instead of that, I can write in this way m raised to ed mod n, right? So now that's why, what is ed? All of you know that. What is ed? So ed, that is, so initially now you know that why I am calculating this ed. So because in decryption side I want to prove how I am getting the plain text. So that's why all this calculation that I am doing. So now instead of ed, what I can write, m raised to, just wait, I can write in this way k5n plus 1 mod n, right? And see, the answer is m. Now again the question is your mind, that is how I am getting this m. Now see, again I repeat this thing so you can understand. So now see, up till now what we have done. So actually I want to prove, that is at decryption side, how I am getting this n. Okay, I want to prove that thing. So here what I am doing here, first all of you know this equation from the key generation, d equals to e inverse mod phi n. Now both the side I am multiplying with e. So what I am getting, ed that is equals to 1 mod phi n. Now see, all of you know that if I am performing ed by phi n, so I am getting some k integers, such that what I am getting, ed minus k phi n, that is equals to 1, right? So now instead of ed, I can write k phi n plus 1. So now I am checking for decryption and I want to prove the n. Okay, so all of you know in decryption side, the equation is c raised to d mod n. So instead of the c, a ciphertext, what you can write, m raised to e mod n, that you can write, right? So now here I can write in this way, m raised to ed mod n, mod n, right? In this way you can write. Now then after, what you have to do? So all of you know ed equals to k pi n plus 1, right? So here instead of this ed, what you can write, k pi n plus 1. So that means the answer is m. Now again the question is in mind, that is how we are getting this m, right? Instead of this m raised to k pi n plus 1, why I am putting the m? Okay, so this is the question. Now what do you have to do? So according to the second version of Euler's theorem, what is the equation? The equation is, just wait. instead of that, why I'm putting this app. So here I can say that according to the second version of Euler's theorem, if n equals to p into q, a is less than n, and k is an integer, then I can write in this way a raised to k phi n plus 1 mod n congruence a mod n. This is the equation, okay, according to the Euler's theorem. Now listen, here in this case what happened? So this is the Euler's theorem that already that I have explained. So according to here in our case, we can say that a raised to k phi n plus 1, n is what p into q, and a is a what less than n, right? And k is an integer. So according to this theorem, I can say that it instead of this you can write congruence a mod n, right? So instead of that directly I am writing this n. Okay, up to this clear, everyone? Is it clear to you all? Okay. Now, uh, sorry. Now, now see here. Here in this case, what happened? There are the three cases. See, all of you know that if A is less than N, so N is a combination of what? N is a combination of P into Q. And if A is less than N, then the three cases you can say that which three cases? Either A, see if A is less than N, then either I can say that A is neither a multiple of P nor a multiple of Q, right? If A is less than N, then can you say that? The second case, A is a multiple of P, but not a multiple of Q, right? Then you can say that A is less than N. And the third scenario, A is a multiple of Q, but not the multiple of P, right? So these are the three scenarios are possible. So now see, one by one through this scenario, I want to prove this thing. Okay, so now see, just you have to understand, okay, when a raised to k phi n plus 1 mod n is there, then how I am getting the a mod n, right? So just I am proving that thing so you can understand. This idea, okay, if a less than n is there, then you have to understand if n equals to p into q, then a is less than n. There are the three cases. Either it's a multiple of p nor a multiple of q, a multiple of P but not a Q, and multiple of Q but not a multiple of Q but not a multiple of P. So these are the three cases. Now start with the first case. And through this particular case, I want to prove this thing. Okay. So how can I prove? Now I will explain you whiteboard so you can understand. Now, for example, see initially, just you have to remember the P that I am taking, that is 11. The Q that I am taking, that is 7. And all of you know that n equals to P into Q. So n, that is 77. And I'm talking about case number 1. So what is case number 1? Is neither multiple of P nor multiple of Q. Right? Now see, all of you know that if A is neither a multiple of P nor a multiple of Q, then what you can say? Then A and N are co-prime. Yes or no? If A is neither a multiple of P nor a multiple of Q, then can you say that A and N are co-prime? Yes or no? Yes or no? Okay. So therefore, I can write in this way: A and N are co-prime, right? Now, so now see the calculation. Now what I want to prove, all of you know that. So now see this one. I want to prove if I am taking a raised to k phi n plus 1 mod n, then how I can achieve this a mod n that I want to prove. Okay, so now I'm taking the first case. If a is neither a multiple of p nor a multiple of q, so that means I can say that a and n are co-prime. And if a and n are co-prime means the GCD of a and n is 1. Right? So now from this equation, how can I prove this a mod n? So that I will show you. So now what I'm doing. So a raised to a phi n plus 1 mod n, right? So now all of you know that instead of this, what can I write? So I can write in this way: a raised to phi n raised to k into a mod n. I can write in this way, right? Now then after, all of you know that according to the Euler's theorem, all of you know that already that I have explained. According to the Euler's theorem, I can say a raised to phi n, that is congruence 1 mod n, right? From Euler's theorem, I can say that. So what can I write here? I can write in this way: 1 raised to k into, instead of this, I am putting 1, right? So 1 raised to k into a mod n, right? So that means here from that I am getting a mod n. So here see, through this concept, the three scenario that I want to discuss. In the first case, if I am taking a is neither a multiple of p nor a pq, so at that time I am getting this result a mod n. Okay. Now next I will show you the next concept. So now see, in the next concept what happened? A is a multiple of P, but see that is if it's a multiple of P means can you write in this way? A equals to I into P. If it's a multiple of P means some I into P. I can write in this form, but it's not a multiple of Q. And all of you know that see, first I am not calculating for this A raised to K phi n mod Q. First I am calculating for A raised to phi n mod Q. Okay, I am not taking this. So now instead of this phi n, all of you know that I can write in this way because n is a combination of p into q. So I can write in this way: a raised to phi p into a raised to into phi q more q. Now instead of that, can I write a raised to 5q more q raised to 5p more q? In this way I can write. And all of you know that. See, a is not a multiple of q. If a is not a multiple of q, then all of you know that the GCD of that two number is 1. And then all of you know that if a and q are relatively prime, or you can say that if they are a co-prime, then you can apply the Euler's theorem. And according to the Euler's theorem, instead of this, I can put one value, right? And see, so that's why I can write a raised to k phi n more q. That is, instead of this, I can put the value 1, and that's why I'm getting 1. And now why I'm writing 1 plus zq? So see, this equation that already that I explained, so instead of this, I can write in this way, right? So same way I'm performing the calculation, and then what I'm getting, a raised to k phi n, that is equals to 1 plus zq. Now see, if a raised to k phi n plus 1, that is equals to, instead of that, I can write the value, that is a in bracket 1 plus zq. Okay, so now what I get, a plus a zq. Okay, so now instead of this, what I can put the value here. So So instead of that, I can write in this way: a plus ij into pq. So what I get? So finally, I get instead of this pq, I can write a plus ijn. And see, instead of this a raised to k phi n plus 1 mod n, what can I write? A mod n plus ij n mod n. And all of you know ij n mod n, that is 0. So what I get? Now a raised to k phi n plus 1 mod n, that is equals to a mod n. Okay, so in this way you can prove it. And see, the case number 3, the proof is similar to the case 2, but the rules of P and Q are interchanged. Okay, so in this way, just I want to show you, okay, if this type of form is given to you, then how you achieve the end. Okay, so there are the 3 different cases that I want to tell you. In each and every case, you are getting A, right? So all of you clear up to this? Is it clear to you all? Okay. Okay, now listen. Next, I will. Okay, now just one topic is remaining, and then after I will give you an example that you have to solve today. Now, see, all of you know that in RSA, if Alice wants to send some message to your Bob, there is a encryption equation C equals to M raised to E mod n, and there is a decryption M equals to C raised to D mod n. And see this problem that in initial lecture that I have discussed that. So if this type of equation is given, then see the eth root of C with respect to modulo n. If you want to find, then it's very hard. It becomes a very hard, and that's why you can say that. See, to find out the eth root of C with respect to modulo n is very difficult, and that's why I can say that the RSA is very secure. This is the one of the reason. The another reason why the RSA secure is generally the three. See, in our example, we have taken a very small number, but normally in real life, what happened? The 300 digit long prime numbers are used to protect against the attacks in RSA crypto system. So let's say you can say that if P is a 300, Q is also a 300 digit, then the n becomes a very large, right? So that means, see, here in our RSA algorithm, all of you know that the n is public. See here, the n is public, but see n is public, but see here you can say that if the n is very large, then it's very difficult for attacker to find out what is the value of p and q. So that is a factorization problem, right? It's very hard. So that's why you can say that the RSA is a secure. So this is another reason. And the another reason and the this is another reason, and the first reason that I have explained. So if this type of equation is given to you, so finding the eth root of C with respect to modulo n, it's very difficult. And see, this is known as a this problem, that is a discrete log problem, and that I will explain you later. Okay, now listen everyone. So now next you have to solve the example. So now see, now I'm not in a position to speak more. So now I will give you example everyone. So you have to solve it, and you have to one by one you have to tell me the answer. Okay. Now let's say, listen everyone, one by one I am asking you a question. You have to tell me what will be the answer. So now let's say in RSA algorithm, E equals to 7 and Q equals to 7, Q equals to 11 is given. Just wait. Okay, these two prime numbers are given everyone. So all of you please write down in your notebook. These are the two prime number that you have to take. Now I will show you algorithm one by one. Calculate it. See, this example can be asked in exam in 6 to 7 marks. So one by one calculate it and tell me the answer everyone. Okay. So I will show you algorithm. So now in this case, if Alice wants to send some message to a Bob, then first of all the key generation is done by Bob. So now first of all I have taken p equals to 7 and q is 11. Okay, now perform this step, and everyone one by one write down the answer in a chat window. First perform this step, the second step, third step, and fourth step, and after that tell me the answer. I will give you a time. Quickly do it and tell me the answer. Once it is done, please unmute yourself and tell me the answer. So what is N, everyone? Please unmute yourself and reply me. What is N?
77.
N is 77. What is phi N, everyone?
60.
Phi N is 60, right? Because it is what? P minus 1 into Q minus 1, right? So what I am getting? 60, right? Now all of you, you have to choose a E such that what you have to do? The GCD of what? The GCD of E comma phi N is 1. So all of you calculate it and tell me the answer. What is the value of E? So have we calculated, everyone? Okay, everyone. I am giving you a value. Let's say, and see, everyone take the same value. Just wait. All of you take E equals to 13. Take E equals to uh, just wait. E equals to 13. Okay. Now what is the next step? Compute D equals to E inverse mod phi n. So what is E? E, that is 13 inverse mod 60. Okay. So calculate it and tell me the answer. You have to take E as a 13. So now compute D equals to E inverse mod phi n. Apply the extended Euler algorithm and tell me the answer. What is the answer of 13 inverse mod 60? Yes, Ricky and Abhi. student. In what you get the answer 37. Okay. What about other students? Abhi, Harsh. Okay. Okay. So listen again. Just I repeat. If I want to calculate 13 inverse more 60, then what I have to do here? This Q, R1, R2, R, T1, T2, and T. Right? Now, what is R1? All of you know that this 60, this 13, Q, that is R1 divided by R2. So what you get 4. What is R? R1 minus Q into R2. So what you get 8. T1 initially you have to take 0. T2 you have to take 1. And what about T? T1 minus Q into T2. So what you get? Minus 4. After that, while R2 greater than 0, continue how to repeat the loop. Now all of you know that there is no need to explain. So now the whatever the value of R2 is there, that is assigned to R1. Then here 8. So here what you get? 1. And here 5. This T1. This value is assigned to T1. Here this minus 4. And then here 5. Now next what I'm doing here, see this whiteboard so you can understand. 8, 5. So you have to continue repeat until the R2 greater than 0. The same process I'm doing, so I'm not speaking anything. Okay. See the whiteboard. 5, 3, this 1. That is what R1 minus R2 in R1 minus Q into R2. So what you get here? 2, this 5, this minus 9, this 14. Right? So then after what you get next? Sorry. 3. And finally, what you get here? All of you are getting the answer up to this? Yes or no? Hello? Can you hear me? Okay, Harsh. Are you getting the answer? 37? Okay. Okay. So now that's why here I am getting minus 23. So what I have to do here? Minus 23 plus 60, and therefore I can say that 13 inverse mod 60, that what I am getting 37. This is my final answer, right? So now after that, what happened? All of you know that this after this, what the probably public key and private key are generated. So now what is my public key? Can anyone reply? What is my public key? What is my public key? Public key, that is what all of you know that it is En. The public key, that is En, right? What is E? That we have taken 13, and N, that is 77. So this is my public key. What about the private key? So private key is what? PQD, right? So here you can say that what is P? P, that is 7, Q, that is 11, and what you get the value of D? The value of D that you are getting, that is 37. So right now what the Bob will do? Bob sends public key to Alice. Okay, now what the Alice will do? So take some plain text. So let's say you can say that the Alice uses a plain text. Some plain text the Alice uses, and let's say the plain text that is m equals to sorry, let's say the m equals to 5, that plain text that I am taking. Right now what the Alice will do? Which encryption algorithm the Alice use? So Alice use C equals to m raised to e mod n. This algorithm the Alice will use. Now what is this equation? And the value of m is 5, the value of e is what? 13, and then mod, what is the value of n? N, that is 77. Now all of you apply the square and multiply method and tell me the answer. I will give you a time. So quickly calculate it. Is there any need to explain the algorithm again? For all of you clear? Okay, so I think all are clear. So now quickly do the calculation, everyone. By using the square and multiply, calculate the answer and tell me the reply me. Once it is done, please reply. What's the answer, everyone? Rikin, actually, in my material that I have written DN, but actually N is a ENN, that is a public key, right? Basically, P and Q is a combination. Means N is what, the combination of P and Q. But see, actually the N is public, and what I'm trying to say, why PQ is private. So in this algorithm, see, basically if any attacker, if it know the value of n, then to see if p and q is very large prime number, then n is what, n is a to crack it, right, to find the factorization. See, all of you know that in this algorithm, just I want to tell you one thing, that is in our algorithm, just wait. In our algorithm, what happened, if attacker know the value, see, suppose the n is public. Now if attacker know what is the value of p and q, then it's very easy to crack this RSA algorithm, because p and q is known, is easily calculate the phi n, easily calculate the e, easily calculate this d value, and see, you can easily encrypt or decrypt it, and you can get the very you can get the plain text message. But in RSA algorithm, what happened? See, normally we are taking the very large number, right? So for our convenience purpose, right now we have not taken. But if it's a very very large, then n is what? N is a n becomes very large. So it's very tough to factorize this, to find out this p and q. This is a factorization problem. It's very tough to find out what is the value of p and what is the value of q, right? So PQD. So in our material that I have written, but you have to consider P, Q, and D. Clear, Ricky? What I'm trying to say? Okay. Okay, good. Answer is 26. You are correct, everyone. So here, the answer that you are getting, that is 26. Okay, now once it is done, everyone, now see, the encryption is done. So now this ciphertext is sent it to the Bob. What the Bob will do? Bob decrypt it with the help of which function? M equals to C raised to D mod N. So now all of you again calculate by using square and multiply, and tell me the answer. So C is 26 raised to D means 37 more 77. So quickly do it and tell me the answer. See, all of you know that actually the answer is 5, right? But see, do the square and multiply method, and then calculate it, and then show me the answer, whether you are getting the 5 value or not. Quickly do it. Is it done, everyone? Done, everyone? Okay. So, are you getting that 5 value original message? Rikin, what about the other student? Is it done? Okay. Then thank you, everyone. Okay, so this is all about RSA algorithm. Now one topic is there RSA attack that I will explain later, and in next lecture onward, start with the Miller-Rabin primarity testing. Right? Thank you, everyone.